Welcome back. In this video, we are going to learn about the mechanism of the wall shear stress that generates at the interface between the inner surface of a straight pipe and the fluid which flows through the pipe. Then we will learn about the force due to the fluid pressure on a plane surface. And finally, we will learn to drive the relationship between the wall shear stress and pressure drop of the fluid flowing through a straight pipe. This question serves as a reference which is from GATE 2013 MESAT A. So let's first read out this question and try to analyze it for what is given and what is asked. For a study fully developed flow inside a straight pipe of diameter d. Alright, so we have a fully developed flow flowing through a straight pipe of diameter d, and the condition is steady state. Alright, let's proceed further. Neglecting gravity effects, the pressure drop delta P over a length L and the wall shear stress tau W are related by. So basically, this question is asking about the relationship that relates the pressure drop delta P with the wall shear stress tau. Alright, let's begin by drawing a diagram of a straight pipe of diameter d. There we have it. We have a side view of a straight pipe of diameter d through which a fully developed flow of a fluid flows with some velocity v in a steady state condition. Since the fully developed flow of a fluid flows through this pipe, the flow pattern of the fluid does not change along the length of the pipe. Alright. Similarly, since the condition of the flow inside the pipe is steady state, the velocity of a fluid at a particular point along the flow does not change with time. Alright, now we would consider two sections at a distance of L along the pipe. So we have two sections, section 1 and section 2, at a distance of L along the pipe length. We would consider a fluid element or a control volume between these two sections and inside the pipe. So this fluid element would be of cylindrical shape of diameter d and length L. So we have the fluid element or control volume CV, and at the section 1 the fluid pressure is P1, and at the section 2 fluid pressure is P2, and this control volume is of cylindrical shape and of length L and diameter D. Alright, in this diagram these green arrows represent the wall shear stress tau W that the internal wall of the pipe exerts on the immediate fluid surface of this fluid element, alright, along its curved surface, alright, because the pipe is in stationary condition and the fluid is flowing in the rightward direction inside the pipe, so there is a relative motion between the fluid and the internal surface of the pipe, alright. So at the interface between the fluid and the pipe there exists a relative motion or slip, alright, because of the relative motion between the fluid and the inner surface of the pipe, alright. That is why this wall shear stress develops at the interface, which acts in the opposite direction of the fluid velocity on the fluid and in the direction of the fluid velocity on the internal wall of the pipe, alright. So this wall shear stress develops at the interface between the fluid and the internal surface of the pipe, alright, and acts in the opposite directions on both the fluid element and on the internal surface of the pipe, alright. In this diagram we have only drawn the directions of the wall shear stress that act on the fluid element, alright, and not on the internal surface of the pipe, because we want to only analyze the forces that act on the control volume or the fluid element that we have considered, alright. This wall shear stress acts parallel to the length of the fluid element along its curved surface in the opposite direction of the fluid flow. The total resultant shear force because of this wall shear stress causes this fluid element to retard in its motion, alright. In other words, the total shear force that would act on this fluid element in the opposite direction of the fluid flow would try to decrease the motion of this fluid element. All right, so that the relative motion between the fluid and the internal wall of the pipe becomes zero. All right, that is why the wall shear stress develops at the interface and acts in the opposite directions on both the immediate fluid and on the inner surface of the pipe. All right, now we know that the curved surface of this fluid element is of a cylindrical shape of diameter d and length L. So the total surface area of this fluid element would be the same as that of a curved surface area of a cylindrical object of diameter d and length L. So this wall shear stress acts on the curved surface of this fluid element, all right, in the opposite direction of the fluid velocity. All right, so the total shear force that would act on this fluid element due to this wall shear stress would be equal to the wall shear stress times the total curved surface area of this fluid element. All right, and we know that the curved surface area of a cylindrical shaped object of diameter d and length L is equal to pi d times L. All right, so the shear stress would act on this whole curved surface area, which is equal to pi d times L. All right, so now we would write the expression of the shear force or the total shear force that would act on this fluid element, all right, in the opposite direction of the flow velocity of this fluid element. All right, all right, so we have the expression of the total shear force acting on the fluid element in the opposite direction of the flow, all right, on the curved surface. So we have the expression of the total shear force that acts on the fluid element in the opposite direction of the flow, right, on the curved surface of the fluid element, which is a cylindrical shape of diameter d and length L. All right, and we know that the shear force is equal to the shear stress times the surface area on which the shear stress acts. And here the shear stress is a wall shear stress which acts on the curved surface area of the fluid element, which is of diameter d and length L. So the curved surface area of this cylindrical fluid element becomes equal to pi times d times L. Alright, so now we would plug the expression of A into this total shear force expression and would write the next step. So after plugging in the expression of A into the total shear force expression, we get the expression of the total shear force. All right, now we have the force, which is a total shear force, which acts on the curved surface of the fluid element. All right, now we would write the expressions of the forces that would act on these surfaces of the fluid element. All right, and these surfaces are actually circular surfaces of diameter d. All right, because when we look from here, all right, then we would see a disk of fluid element of diameter d. All right, and similarly here, when we would look from here, we would see a disk of a fluid of diameter d. All right, and just the immediate vicinity of these circular surfaces of diameter d are the pressures of the fluid outside of this fluid element are P1 and P2. Now we would write the expression of the pressure force F1 that the fluid on the section 1 would exert on this surface of the fluid element. All right, all right. So we have the expression of the pressure force F1 on fluid element at section 1. All right. So the pressure force F1 due to the fluid pressure at section 1 acts on this surface, which is a circular surface of diameter d. All right, in this direction, because we know that the force due to a fluid pressure acts perpendicular to the surface. All right, and we also know that the force due to fluid pressure is equal to pressure times the surface area, all right, on which the pressure acts perpendicularly. All right, this pressure P1 exists at the section 1 and this pressure exerts a force perpendicular to this surface. All right, and the total or the resultant of the pressure forces on this surface due to fluid pressure P1 becomes equal to the total pressure force F1. All right, which would act in this direction, and the A is the surface area of this circular surface on which the pressure P1 acts. All right, which is equal to pi by 4 times diameter square. Therefore, a force due to a fluid pressure on a plane surface is equal to the pressure times the surface area of that plane surface on which the fluid pressure acts perpendicularly. Alright, and the direction of that force becomes equal to the resultant of these pressure forces on the plane surface, which would, in case of plane surface, be the same as the direction of the pressure. Alright, so here at section 1, the pressure P1 would act in this direction. Alright, in this direction. So the direction of the force F1 would also be in this direction, in the direction of the pressure P1. Alright, and the sum of these small forces that the pressure P1 exerts on the plane surface areas of this total circular surface becomes equal to the total pressure force F1, which is given by pressure P1 times the total surface area of the plane surface, which is a circular surface A equal to pi by 4 times d square. Alright. Similarly, we would write the expression of the pressure force on this fluid element at section 2. Alright. Alright, so we have the expression of the pressure force on the fluid element at section 2. Alright, which is equal to F2 that acts in this direction. Alright, perpendicular to the circular surface. Alright, and is equal to P2 times A, where A is the surface area of this circular surface of diameter d, and is equal to same as this surface area pi by 4 times d square. Right, now here the total pressure force F2 would act in this direction, right, on this circular surface. Alright, because we know that the pressure force acts perpendicular to the surface. Alright, so the fluid pressure at the section 2 would exert pressure forces in this direction. Alright, and the sum of those small pressure forces on this whole circular surface would result in this total pressure force, which is F2, and becomes equal to the pressure P2 times the total surface area, alright, at the section 2, which is equal to the surface area of a circular surface of diameter d. Alright, now as we can see here that the flow of the fluid is fully developed inside the straight pipe, and the condition of the flow is steady state. Therefore, there is no acceleration of the fluid element. Alright. In other words, the fluid elements moves with the constant speed or velocity in the direction of the velocity of flow. Alright. So this fluid element moves in the rightward direction inside the pipe with a constant velocity or speed, all right, because of the steady state condition, all right. In other words, the velocity of this fluid element does not change with time, all right. The wall shear stress tau w remains constant over the curved surface area, all right, because of the fully developed flow, meaning the condition of the fluid that exists at this point remains the same along the flow. So the same wall shear stress exists everywhere at the interface between the fluid element and the inner surface of the pipe. All right. Now, as I was explaining that the fluid element is moving with the constant velocity or speed v because of the steady state condition, the net force, all right, on this fluid element must be zero, all right, because we know from the Newton's second law of motion that if an object or a matter moves with a constant velocity, all right, or a constant speed in a fixed direction, then the net force on it must be zero. Therefore, in this case, the net force on this fluid element must also be zero. All right. So we would balance the leftward forces that act on this fluid element with the corresponding rightward forces, all right, that acts on this fluid element. So now we would only balance the forces on this fluid element in the direction of the flow, all right. To balance the forces, we would equate the sum of the leftward forces that act on this fluid element, all right, with the sum of the rightward forces that act on this fluid element, all right, and write the force balancing equation, all right. So balancing forces on the fluid element along the pipe, all right. So we are going to balance the forces that act on this fluid element along the pipe, all right. So what we would do is we would equate the total rightward force with the total leftward force, all right. And we know that there are actually three forces that act on this fluid element. One is the F1 force, which is the pressure force on the circular surface of the fluid element due to pressure P1, and F2 force, which is also a pressure force due to the pressure P2 on this circular surface. And third one is the shear force or total shear force, that acts in this leftward direction on the curved surface of the fluid element, which is a cylindrical. Right. So the total rightward force is equal to F1. Alright. And total leftward force is equal to F2 plus this total shear force, that is Fs. Alright. Alright. So we have the force balance equation. Now we would plug in the expression of F1, which is P1A, and F2, which is P2A, and Fs, which is equal to this. Alright. And write the next step. So we have the next expression. Now we would plug in the expression of A. Alright. That is surface area of the circular surface of diameter d. Alright. Which is equal to pi by 4 times d square into this expression. And would write the next step. Alright. After plugging in the expression of A, we have the next expression. Now we would rearrange it. Alright. After rearranging, we have this expression. Alright. Now we would further simplify it. Alright. Alright. After simplifying this expression, we have the next expression. Right. Now, as it is given that the pressure drops along the length L of the pipe as the fluid flows, so P2 is smaller than P1. Right. And we can also see that from our expression here. Alright. So for this quantity to be positive, P1 must be greater than P2. And this is caused by the wall shear stress. Alright. So wall shear stress actually decreases the fluid pressure as the fluid flows through the pipe. Alright. Now we would assume that the pressure drop is delta P, that is P1 minus P2 is equal to delta P. Alright. And would write the next step. Alright. Alright. We have replaced P1 minus P2. Alright. With delta P, which is the pressure drop along the length of the pipe. Alright. Now we would further simplify this expression by cancelling out pi from both sides and d from both sides, and would write the next simplified expression. Right. So we have the simplified expression. Now we would rearrange it to find the expression of tau w, right, which is the wall shear stress. So after rearranging the expression of tau w, which is the wall shear stress, is equal to this expression. All right. So from the given options, the correct option is option A. All right.